Why does partially full RAM cause lag? Why does partially full RAM, let's say 80%, make the device lag a lot, even though there is some space available to store more data? What I expect is that it keeps working well till 99%. I notice that on the mobile more than on the PC, as it has smaller RAM. For example, my mobile has 2 GB RAM. When I have less than 1 GB of RAM free, it lags a lot. Why does that happen, even though it still has 1 GB to use?
There is much involved here, but I will try to explain it as simply as I can and in a way applicable to just about any OS. There are two basic principles here. The sum total of everything that needs to be in RAM, and those things that would benefit from being in RAM, is almost always greater than the size of RAM. Things that would benefit from being in RAM include process working sets and the standby list. The latter contains data and code that was once in active use, but has since lapsed into inactivity. Much of this will be used again, some of it quite soon, so it is beneficial to keep this in RAM. This memory acts as a kind of cache, but is not really essential, so is in the category of available memory. Like free memory, it can be quickly given to any program that needs it. In the interests of performance, standby memory should be large. The frequency of use of memory blocks is far from random, but can be predicted with considerable accuracy. Memory is divided into blocks, often 4K bytes. Some blocks are accessed many times per second while others have not been accessed for many minutes, hours, days, or even weeks if the system has been up long enough. There is a wide range of usage between these two extremes. The memory manager knows which blocks have been accessed recently and those that have not. It is a reasonable assumption that a memory block that has been accessed recently will be needed again soon. Memory that has not been accessed recently probably won't be needed anytime soon. Long experience has proven this to be a valid principle. The memory manager takes advantage of the second principle to largely mitigate the undesirable consequences of the first. To do this, it does a balancing act of keeping recently accessed data in RAM while that keeping rarely used data in the original files or the page file. When RAM is plentiful, this balancing act is easy. Much of the not so recently used data can be kept in RAM. This is a good situation. Things get more complicated when the workload increases. The sum total of data and code in use is larger, but the size of RAM remains the same. This means that a smaller subset of this can be kept in RAM. Some of the less recently used data can no longer be in RAM, but must be left on disk. The memory manager tries very hard to maintain a good balance between memory in active use and available memory. But as the workload increases, the memory manager will be forced to give more available memory to running processes. This is not a good situation, but the memory manager has no choice. The problem is that moving data to and from RAM as programs run takes time. When RAM is plentiful, it won't happen very often and won't even be noticed. But when RAM usage reaches high levels, it will happen much more often. The situation can become so bad that more time is spent moving data to and from RAM than is spent in actually using it. This is thrashing, a thing the memory manager tries very hard to avoid, but with a high workload it often cannot be avoided. The memory manager is on your side, always trying its best to maintain optimum performance, even under adverse conditions. But when the workload is great and available memory runs short, it must do bad things in order to keep functioning. That is in fact the most important thing. The priority is first to keep things running, then make them as fast as possible.
All modern operating systems use otherwise unused memory for caching data so that it can be accessed from fast RAM instead of slower storage. They will generally report this as free memory, since applications can clear the cache and use it if they need to, but it's still actually being used. The less of it there is, the less data can be cached, and the slower the computer will be.
This answer has been mostly rewritten to reorganize the structure and make the message clearer. I have also opened it as a community wiki answer, feel free to edit. Paging is a memory management scheme through which fixed-size blocks of memory have processes assigned to them. When memory usage rises to a high level, i.e. 80% capacity, paging begins to extend from RAM into VRAM, virtual RAM. VRAM is located in system storage, usually within a hard drive, or other sizable storage locations. Processes are assigned part of your hard drive to run as memory and will treat their section as RAM. This is a perfectly normal process. However, when the time spent to transfer data to and from the VRAM increases, system performance decreases. While dedicated RAM is accessed directly through the motherboard from the CPU, which provides a fast connection, virtual RAM must traverse cabling between the board and the location of the VRAM. This, however, causes only slight performance impact. When the rate at which paging to VRAM takes place increases drastically, when dedicated RAM approaches capacity, thrashing takes place. Thrashing is the practice of quickly and rapidly transferring pages of memory into your virtual memory. This takes a huge toll on performance as more time has to be spent fetching and addressing data. Let's say, you want to write down a number 30 digits long. You could either sit next to your screen with your notepad and write it, using the dedicated memory, or you remember chunks of 5, run into the next room and write it down on your notepad in there, using virtual memory. Both get the job done, but which is going to be quicker? Find out more about thrashing here. A big thanks to the contributors of this answer including Daniel B., Zenoid and John Bentley.
Remember, hard drives are an order of magnitude slower than RAM, and RAM itself isn't all that speedy to begin with, in overall architecture. In order of speed of access, where each rung is an order of magnitude slower than the one above, you have processor registers. In practical terms, registers are available within one processor cycle. Considering that processors do billions of cycles a second, 3 and NBSP, GHz equals 3 billion cycles per second, this is crazy fast. Processor cache depends on the level, but these are still pretty fast, 3 to 5 cycle availability for L1 cache. Random access memory, RAM, the random part means you don't know what state it's in when you access it. Think of a package delivery man who has to stop, pick the package up, walk to the door and ring the doorbell and wait for a response. Maybe you don't wait at all, or maybe you wait a minute or two for Mrs. Smith to shuffle to the door for the back of the house. In practical terms, we're talking anywhere from 14 to 27 cycles, depending on what state the RAM was when we accessed it. Hard disk drive. There's a physical process here now, and while it happens as fast as possible, you're waiting for heads to move and tracks to move under those heads. In practical terms, a 7,200 revolutions per minute HDD can complete a revolution in about 4 milliseconds, or somewhere around 750,000 cycles for a 3 and NBSP GHz processor. That's slow. The Virtual Memory Manager is a gambler. It's betting you don't need all of your RAM all of the time, so it makes an educated guess and rolls the dice that your document program which has been in the background for the last 10 minutes while you read this, isn't really important and it shoves it to the HDD. But then you click back to the document. Now the VMM has to load all that data back from the HDD. Worse, if you're low on RAM, it now has to push other data, more gambling, to the HDD to free up usable space. Linux likes to live on the edge here. It will fill the vast majority of the RAM with frequently used data, great for servers with few processes.
If you want to support the channel, please consider subscribing.